Hello students, welcome for our fourth lesson in electrochemistry, and we are still dealing with the first part, which is actually redox reactions. The objective of our lesson today, at the end of this session, you must be able to define oxidation number, and you should be able to calculate oxidation number of elements in combined states. Now, so we are dealing with the redox reactions, but now we are going to define the redox reaction based on oxidation numbers. And from your Form 2 work, you know that oxidation number is the number that is assigned to an element in a chemical combination. It represents the overall charge, the net charge of that element in its combined states. That is what we call the oxidation number, or we can call it oxidation state. Now, moving on, we have rules that we use in giving oxidation numbers to elements. We have rules that we follow. So we are going to look at those rules one at a time. And the first rule is that oxygen in its combined state or in its molecular state is normally assigned -2. So oxygen is normally given -2. Why? We all know that oxygen normally gains 2 electrons to become stable. So oxygen normally ends up having a charge of -2. So the oxidation number of oxygen is -2, except where? Except in peroxides. In peroxides, oxygen is given -1, like in hydrogen peroxide, potassium peroxide, sodium peroxide. So in all these peroxides, hydrogen is given an oxidation number of -1. But in all other compounds, it is normally given -2. The rule number 2, the oxidation number of hydrogen, when we are dealing with hydrogen, hydrogen is normally assigned either -1 or +1, depending on which element it is bonded to. Hydrogen bonded to a metal is normally assigned -1. So like in the hydrides, that is sodium hydride, potassium hydride, lithium hydride, calcium hydride. In all these elements, all these compounds, hydrogen is assigned -1. Now, the same hydrogen, when combined to electropositive, electronegative, when hydrogen is combined to electronegative elements, when hydrogen is combined to electronegative elements, it is normally assigned +1. It is normally assigned +1. Like where we have hydrogen fluoride, water. So when hydrogen is bonded to highly electronegative elements, and electronegative elements are nonmetals. They are nonmetals. So where hydrogen is bonded to a nonmetal, it is normally assigned +1. That is our second rule. The third rule is about molecules. The third rule is about molecules. So like on my screen, all atoms and molecules of elements have oxidation number of 0. Molecules, like when we talk of oxygen molecule, it is given 0. Chlorine, something like chlorine, something like hydrogen, something like nitrogen. So elements which are in combined state, in molecular states, are normally assigned 0 oxidation number. Then we move to rule number 4. Yeah, that table is just an example showing the atoms, free atoms, and also molecules. But when we move to rule number 4, all combined metals and nonmetals, have oxidation numbers equal to their valency or oxidation state. All combined metals and nonmetals have oxidation numbers equal to their valency. Alright, let's look at this table. A case where we have iron 2 sulfate, like in the first column we have iron 2. A case where we have iron 2 sulfate, the valency of iron 2 is 2. So the oxidation state of this ion here is positive 2, equivalent to the valency. If we are talking about iron 3 chloride, the valency of iron 3, when we talk of iron 3 chloride, the valency is this number in brackets. So the valency here is 3. If this ion has a valency of 3, then the oxidation state is positive 3. Now we come to something like sodium. Let us say we talk of sodium oxide. Here the valency of sodium is 1. So its oxidation state or number is positive 1. That's the meaning of that rule. And that rule is very clear that all combined metals and nonmetals have oxidation numbers equal to their valency. So you just check the valency, and that valency will give you the what? The oxidation numbers. We move to the 5th rule, the sum. So in that 5th rule, the sum of oxidation numbers, of atoms, of elements making a compound is equal to 0. The sum, meaning if I have copper 2 sulfate, copper 2 sulfate is made up of copper, sulfur, and 4 oxygen atoms. So if you take the oxidation number of copper, you add to the oxidation number of sulfur, then you add to 4 times the oxidation number of oxygen, you will get 0. So the sum of oxidation numbers of atoms of elements making a compound is equal to 0. Like if we take another example, sodium sulfates. You add the oxidation number of sodium times 2 for sulfur, and then for the 4 oxygen, you will get 0. A total of 0. That is also a very important rule in dealing with oxidation numbers. We look at an example on how to apply such rules. Then number 6, for polyatomic ions or radicals, the sum of the oxidation numbers of the constituent atoms is equal to the charge on that ion. Polyatomic. Polyatomic means these are ions made up of more than one ion. Like this is more than one atom. This is one atom of sulfur, 4 atoms of oxygen. So for polyatomic ions or radicals, the sum of the oxidation numbers of the constituent atoms is equal to the charge. This is the charge. So if you add the oxidation number of sulfur plus the oxidation number of oxygen times 4, because we have 4 oxygen, this one should give you the overall charge, which is -2. Take another example of ammonium, polyatomic. If you take the oxidation number of nitrogen, you add to oxidation number of what? Of hydrogen. But how many hydrogen? The hydrogen have 4. So you multiply by 4. Then you get the overall charge, which is +1. So that is what the rule is telling us. Then, so those are the 6 rules that we are going to rely on. Those are the 6 rules that we are going to rely on when calculating oxidation numbers. So let us look at the first example. Like if you are told you are given copper 2 sulfate. If you are given copper 2 sulfate, it means copper 2. See, when you talk of copper 2 means the valency, not the valency, but yeah, the valency is 2. But the oxidation number is +2. So if we don't know sulfur, we can actually get sulfur by applying one of the rules. So we'll take copper to be +2 plus. We don't know sulfur. Let's say we don't know sulfur. Then oxygen, we are told in any combined state, oxygen is -2. Then we multiply by 4. So this one should give us the overall charge. And the overall charge on this compound is 0. So the sum of the oxidation numbers of the elements forming a compound is 0. So we'll say this is +2 plus sulfur -8 is equal to 0. So sulfur will be equal to +8, take this 8 the other side, -2. So sulfur is equal to +6. So if you add +2 +6 for sulfur -2 times 4 for oxygen, you get what? 0. We move on to another, like here on our screen is a very good example on our screen. Here we are told to determine the oxidation number of nitrogen in. So we want to get nitrogen. Our main problem is nitrogen. In what? A, nitrogen, 2 oxide. Now, oxygen, we know that oxygen is -2. Nitrogen, we don't know. So if we take nitrogen plus the oxidation number of oxygen, which is -2, you get the overall charge, which is 0. So nitrogen, in fact, it is nitrogen now plus and a minus will give you a -2 is equal to 0. So nitrogen is equal to +2. So this is nitrogen in nitrogen 2 is +2. Now this compound, that's why this compound is called nitrogen 2 oxide. That is its name. Then when we go to example, the second example, that is B, nitrogen 4. So for nitrogen 4, let me do it down here. Nitrogen we don't know, but oxygen is -2. How many are they? They are 2. The overall charge is 0. The overall charge is 0. So it will be nitrogen -4 is equal to 0. Nitrogen is equal to +4. So this one is called nitrogen 4 oxide. Now you can see where this +4 is coming from. Nitrogen 4 oxide. That one you can see on the screen. Then in Form 3 we also came across this compound here. We came across that compound, other nitrogen and its compounds. So nitrogen we don't know. Let us say nitrogen is Y. Nitrogen is Y. How many are they? There are 2. 2 nitrogen atoms, so we multiply by 2. Plus oxygen is -2. Oxygen is -2. This one should give us 0. So we have 2y minus 2 is equal to 0. So we have 2y is equal to +2. Then we divide by 2, we divide by 2. So y is equal to +1. That's why this compound is called nitrogen 1 oxide. So you can see where the name comes from, nitrogen 1 oxide. We can also give the example of sulfur. We can also give the example of sulfur in different compounds. So we want to deal with sulfur in A. Sulfur in what? Sulfur in sulfur 4 or in SO2. Let me call it SO2. Like that. So we don't know sulfur. We fix sulfur in Y. Then plus oxygen. The rule tells us that oxygen is -2. How many are they? There are 2. Is equal to 0. There is no charge. So the charge is 0. So we'll have y -4 is equal to 0. Y is +4. That's why this compound, therefore, the name is sulfur 4 oxide. The name is sulfur 4 oxide. We have B, the second example, sample after that is SO3. We fix sulfur to be Y. Oxygen to be -2. How many are they? 3. Then the overall charge, there is no charge here, so we say it is 0. So it is Y -6 is equal to 0. So Y is equal to +6. How do you call this? You call it sulfur 6 oxide, like the way it is shown on our screen. Sulfur 6 oxide. We can do the same with the third compound. So we are calculating sulfur in H2SO4. What is the charge of this compound? 0. There is no charge. So hydrogen here is positive 1. Why? Because hydrogen is bonded to electronegative elements. It is bonded to electronegative elements, bonded to nanometals. How many hydrogen? There are 2. Plus, do we know sulfur? We don't know. Plus, oxygen is negative 2 times 4. The overall charge is 0. Overall charge is 0 because the oxidation number of elements in a compound, when the numbers are added, you get 0. That is the law that we are applying here. So this is positive 2 plus y minus 8 is equal to 0. So y is equal to positive 8. Then we bring to the other side. Y is equal to positive 6. And that is why this acid is called sulfuric 6 acid. That's why it is called sulfuric 6 acid. So now you can see where the 6 is coming from. It is the oxidation number of sulfur. You can do again the same for H2SO3. Then you give that compound a name. You come to carbon, you can calculate the oxidation number of carbon in CO2. You apply the same thing we have been doing here. You can also do the same for CO. This is the compound of, which has got 1 carbon and 1 oxygen. Then you give it a name. The same you can do with H2SO3. And then you give it a name. The same can apply to manganese in MnO2. So get that one, you can see the same trend. Then when we come to chromium, you can calculate that in the potassium dichromate. Then come up with the name. Then there is that one too. So let us conclude by giving definitions of oxidation and reduction based on change in oxidation states. So oxidation can also be defined as an increase in oxidation numbers, while reduction can be defined as a decrease in oxidation numbers. Redox reactions can also be said that they are reactions that involve both an increase and a decrease in oxidation numbers taking place at the same time, or simultaneous increase and decrease in oxidation numbers. Therefore, an oxidizing agent is the substance whose oxidation number decreases. A substance whose oxidation number decreases. While a reducing agent is a substance whose oxidation number increases. In our next session, we are going to use the concept of oxidation numbers to identify oxidation processes and reduction processes. And after that, we'll also be able to identify oxidizing and reducing agents. So that is the end of our class today. Let us meet during our 5th lesson. I hope you have enjoyed the lesson.